Welcome to the demonstration of the Applied AI coursework evaluation. The selected domain for the analysis and implementation of AI techniques is hospitals and medicines. According to the literature review that has been conducted, it is evident that AI has been widely used in different kinds of applications in this domain. Some of them include analysis of medical imaging using AI techniques, disease detection using image segmentations, personalized medicine using artificial neural networks and SVMs are some of the most common applications that are seen within this domain. So this is a diagram which shows an precision medicine example which has already been implemented and is used within the industry. The selected application for further analysis and implementation is skin cancer detection using ML and deep learning techniques. For the comparison and the evaluation of AI techniques, I have selected three main techniques. Those include convolutional neural networks, k-means clustering, support vector machines. For more details about each of the techniques, you can go through each of these sections and read about the findings. To summarize about all the three techniques, I have come up with a table over here. So it speaks about the three different algorithms with the input data, the expected outcomes, and the applications in which skin cancer detection can be used by CNN, k-means clusterings, and SVMs. CNN are better suited for skin cancer detection due to the ability of automatically learning relevant features from image data and handling complex patterns to adapt to variations in images, which is lacking in k-means clustering and SVMs. Hence, CNN is selected for implementation and further evaluation of the problem. Moving on to the implementation of the system, first I have created the high-level architecture diagram. So this consists of the data input layer, the model training layer, and finally with the model evaluation and the prediction. So I have come up with the model according to what is designed in the high-level diagram. So let's move forward. First we have the data input part, which first includes the collection of data. So the data set I've used is from Kaggle, which consists of a vast amount of images which are suitable for skin cancer detection. And first of all, I have imported the required libraries, and also the Kaggle dataset is directly downloaded from Kaggle to the Google Colab. And then I have inspected some data from the dataset that I've used. So this is a first 10 lines which is in the CSV file that I've downloaded over here. And next I have also 7 classes in this data set, and the total number of images that is seen is 10,015. So if you take a look at the lesion types over here, we can see that melanocytic navy is in excess, which is 6,705. It's comparatively very higher than the other images. So this states that the data set is unbalanced, and this needs to be taken into care of in the future. Next is a data pre-processing step, which includes image resizing, data augmentation, and balancing of the data set. This is an example indicating the resizing of images to make sure that all the images consist of a uniform input size for the model. This also reduces the computational complexity of the model. Next, I have also implemented data augmentation. This is also performed to expand the diversity of the data set with the application of various transformations. So as you can see, I have provided some examples of some augmented images, and the images of the data set are similarly augmented. So next, the problem was the data set was imbalanced. For this problem, class weights are provided to make the data set balanced. Next, we have the data splitting section. The data set is split into 80% training and 20% test data, which are randomly split. And over here I have visualized some of the images with their related labels. As you can see, we have melanotic nevi, and then we have basal cell carcinoma, and similarly we have different set of images with the relative labels along with the image. Next is a most important part of our process, which is the model training. So the model is defined as a CNN built using Keras sequential API. It consists of a series of convolutional layers followed by batch normalization and max pooling to reduce partial dimension. It also helps to prevent overfitting of the model. Overall, the model incorporates a deep architecture with several convolutional layers followed by dense layers with dropout, ensuring effective feature learning while minimizing overfitting of the model. Moving on to the most important part of the model. So over here we have training the model, and moving on to the main part, the training parameters that I've used is a batch size of 32 and 50 epochs. I have also made sure to save this model to the drive to make sure that the model can be loaded for further evaluation in the future. So as you can see, the model is training with the first epoch, and let's see how the training goes on. So you can see that the training has come to the final stage. The training was continuously carried out and it has reached the 50th epoch. Early stopping was used with the patient's value of 5, but the training has been continued until the 50th epoch. This provides an idea that the model has a minimum risk of overfitting. And we can see the 50th epoch still running. So let's wait until the training stops from the 50th epoch. Several strengths were identified in the CNN model that I've developed, and some of them include high class accuracy for critical categories like melanoma and benign keratosis like lesions, and rare classes also were classified efficiently. So to balance the data set, we have used class weights and also data augmentation. The relative small gap between the training and validation accuracy indicates that the risk of overfitting of the model is very minimized. Several limitations of the system have been identified, and they include misclassification of similar classes like melanocytic nevi and melanoma. This can cause a significant problem in detecting skin cancer using CNNs in the real life. And also there's a noticeable gap between training and validation losses, which indicates a slight overfitting, and this suggests that the model learns from the training data better than the validation data. We have come towards the concluding sentence of the demonstration. Thank you so much for listening to me.